In this chapter, we're going to be talking about query performance and indexing. So what are the different things that impact the performance of queries? Firstly, of course, there's the underlying hardware that the database is running on. So things like the disk speed, the memory, or the CPU will impact the performance. There's also different ways that you can tune Postgres for different performance characteristics. By default, it won't necessarily have the most optimal tuning. There's the load that the database server is under. How many different connections is it handling, and how many different queries it's running concurrently. Of course, there's the volume of data you're requesting and the size of the tables that you're working with. And finally, there's the query itself. How is the query written? How is it utilizing various indexes? And so on. In this and the next few videos, what we're going to focus on is just the queries themselves. We're going to look at how to read what are called query plans, and in particular, how indexes can help us obtain large performance gains. Your first task is typically to identify which queries are performing poorly. It could be in the simplest case that you've written the query yourself, and you can see right away whether it performs well or not. It could be that you're building a web application or mobile app, and you find that a particular action in your app is quite slow, like opening a page or interacting with a button, and you need to walk through your code to identify the underlying queries that are being run when you perform that action. If you're running your database in production, what's also useful is to enable logging, and then you can look at those logs after the fact to identify poorly performing queries. Note that by default in Postgres, logging is turned off. To enable it, you have to edit what's called your PostgreSQL configuration file. There's lots of great guides online that go into the nitty-gritty of how to set up your logging, but you can see here at least a basic setup which will get you going. Okay, so let's say that you've identified a query that's quite slow. Either you ran that query yourself and you weren't happy with its performance, or you'd looked in your logs and you found one query that is really quite slow, and you want to understand why and fix that. The best way to do that is to look at what's called a query plan. All throughout this course, we've been talking about SQL as a declarative language. You declare what you want in SQL, and then something called a planner or optimizer figures out the best way to get what you want done. A query plan is a report on how the database plans on executing your query, a step-by-step description of which indexes it will use, the order of table joins, how it's going to scan the table to retrieve the data, sometimes even how many rows it expects to look at while performing the operation, and much more. The planner evaluates your query and considers different possible execution plans. It's going to evaluate the cost of all of the different ways it could get the data that you're after, and then pick the best one and run it. So if you understand a query plan, then you can understand why your query might be slow. You'll essentially understand how, under the hood, the query is being executed, and just how the database is attempting to fulfill your request. In Postgres, you can use the explain command to obtain the query plan for a given query. Let's start with a really simple example. We'll start with a query that returns us all the actors with a first name of Mary. If we were to run that query, we find that there's two actors. How can we obtain the query plan for this query? What we do is add explain to the beginning. This is now all one single statement, so we can run this, and we obtain our query plan. I'll explain this output shortly. Before I do that though, one thing that's important to note is that using explain alone didn't actually execute that query. When you use the explain command and give it a query, all the database will do is give you the query plan. How it would go about executing this query if it actually were to be run. But the query isn't actually being run. The database didn't actually go to the actor table and search it for all the actors with the first name of Mary. If you want to both see the query plan and actually execute that plan at the same time, you can use explain analyze. Let's do that now. Notice that when we ran this now, we got some additional information. We got the actual time and some additional information about the number of rows that got removed. We got the planning time, and we got the execution time. What this means though is that if you want to run explain analyze on a query that will perform some kind of modification of your database, you should perform that within a transaction that you then roll back. For example, let's say that I'm trying to analyze and understand an update statement. I'll do a very simple one. So this is a query that if I were to run would actually update the actor table and update the last update column. I could use explain analyze because I want to obtain the query plan for this and I want to analyze the actual runtime of it. But because I'm just investigating this, I don't actually want it to be permanent. So what I might do then is perform it within a transaction block that I roll back. So I'll write begin, and I'll start the transaction. I'll run this explain analyze command so that I can understand how the actor table is being updated. I've got the information I wanted, the actor table was updated, but I can now roll back because I performed this all within a transaction block. Okay, so let's return back to our original query. Let's drop analyze for a moment, and let's talk about the different components of the query plan. Firstly, this query plan just involves a single step, the sequential scan on the actor table. In future videos, we'll see plans that involve multiple steps, but this is a pretty simple case, so we just have the one. A sequential scan on the actor table means that this query would just involve reading the entire actor table from disk, and then after doing that, it performs a filter on the output, filtering for all the rows where the first name is Mary. Usually a sequential scan is a pretty inefficient way to go about retrieving data. The entire table had to be read from disk, and reading from disk is quite slow. In a coming video, we'll look at indexes and how indexes can allow you to retrieve data in a more efficient manner. So after describing this step, sequential scan on the actor table, there's a bunch of different values here. Firstly, there's the cost, and the cost is given as a range. The initial value is the estimated startup cost, and the final value is the total cost of the step. The startup cost, which in this case is 0, is the cost of any work that needs to be done before retrieving the data from the disk. So the scanning of index, joining of tables, sorting, etc. When you're talking about a sequential scan, the startup cost is 0 because there is no pre-work that needs to be done before going to disk and grabbing the data. One thing that's important to note is that the cost measure is actually a fairly arbitrary unit, and it varies depending on the hardware and how your database has been set up. The main idea is that the query planner has shown you the plan that it thinks has the minimum cost. The larger the value here, the higher the cost and the more expensive the query is. The rows is the number of rows that it thinks that this step will return. Here we've filtered by actors with a first name of Mary, and the query plan thinks that this sequential scan with a filter is going to return 2 rows. Finally, the width is the number of bytes that it thinks the row will be. So if you're selecting all the columns from the actors table, you're filtering by only those actors that have a first name of Mary, what the query plan is telling you is that it thinks it's going to return 2 rows, and each of those rows will be 25 bytes in length on average. At this point, you might be thinking, how does it know that this step is going to return 2 rows? That is, how does it know that there's going to be 2 actors with a first name of Mary without actually executing the query? Postgres actually maintains information about your tables that it calls statistics. So for each of the different tables in your database, there's a corresponding table that's holding on to statistical information, like the number of rows in that table, the number of distinct values in certain columns, the most common values, and so on. The query planner actually uses those table statistics to inform its plans. So even though the query isn't being run by using the statistics, the query planner was able to estimate that this query would return 2 rows. So this is the really important point then. The query plan is just an estimate based on the statistics that are available to the planner. It's only when we add analyze that we actually truly run the query and then get the true number of rows returned. And so sometimes you'll find that's different from the query plan's estimate. So let's go ahead and add analyze back in. Let's run this. So by adding analyze back in, we now got some additional information. The original query plan remained unchanged, so all those values are the same. What we got now was the actual time in milliseconds that the query took to run. We get a range, which again corresponds to those different cost values. So this 0.016 milliseconds is the startup time, and this 0.024 milliseconds is the actual time that it took for this step to run. There were, in fact, 2 rows that got returned, so that matches the estimate, so that's good. And loops here refers to the number of times this step was run, which doesn't really make sense here, but in future videos you'll see steps that get run multiple times. Finally, we get the planning time, because actually for a database to come up with a query plan takes time itself, and that's part of the overall time that it takes to execute a query. And then finally, there's the execution time as well, which is how long it took to actually then execute the query. One thing that's important to note about this timing data is that Postgres will internally cache both query plans and data. So if you run the same query twice in a row, for example, you'll often find that the second time will be much faster due to the cached plan and data. Okay, so now we know what a query plan is, and we know how to obtain the query plan for a given query. Before we can dive into more complex plans and understand how to read and interpret them in more detail, let's first take a little detour and talk about indexes.